Welcome back to this next video in which we are discussing group homomorphisms. Okay, so firstly let me just apologise for the abrupt ending to the previous video. There was an interruption and I had to remove the ending to the previous video, okay, which is why it ended quite suddenly and why there is some writing here that wasn't there at the ending of the previous video. Okay, so let me just go over then what I've written here. So remember what we were trying to do? We were trying to prove that the image of a homomorphism in phi here is always a subgroup of the codomain group G'. Okay, right, so we wanted to prove that indeed that subset, the image of the homomorphism, with the inherited composition law from the codomain group, forms a group. So we needed to prove that it obeyed the axioms of group theory. Okay, so we've done closure, we've done associativity, we've done the identity element, all we've got left is inverses. Okay, right, so what I'm going to do is I'm going to say, let's say we've got some arbitrary little element here, little a prime, which is an element of the image of the homomorphism. So just take an arbitrary element in the image of the homomorphism. What I want to prove is that its inverse element is also an element of the image of the homomorphism. What I know is that because A' is an element of capital G', since the image of the homomorphism is a subset of capital G', so A' is certainly an element of capital G', and because capital G', the codomain group, is a group, there must exist an inverse to little a prime within the codomain group, and I've called that little a prime inverse here. Okay, so what I want to show basically is that this inverse element for this arbitrary little a prime, which is in my image of the homomorphism, I want to show that that's also in the image of the homomorphism basically. Okay, so what I can now do is I can say, okay, let's write little a prime as equal to phi of some a. Okay, so because little a prime is in the image of the homomorphism, I can write it as phi of some little a, where little a is an element of my domain group. We've had that argument before, we've seen that argument before, okay, when we were doing closure. Okay, and then what I can say is I can rewrite now little a prime inverse as being phi of a inverse, okay, because it's the inverse of this element phi of a. But we had a theorem about phi of a inverse, basically like this. Okay, we had shown that phi of a inverse is the same thing as phi of little a inverse here, basically. So what I can now do is I can rewrite this as being phi of little a's inverse, basically. Okay, and therefore what I have done is I have shown you that indeed little a prime's inverse must be an element of the image of the homomorphism. Okay, because, let me just put that in there. Okay, because this is an element of the domain group, capital G here, and we are taking phi of that to get little a prime's inverse. Okay, so that means that this is some element in G mapped onto it with the homomorphism phi, basically. So now we know that little a prime's inverse is also an element of the image of the homomorphism. Okay, right, so what I have just proven to you then is that if you have some arbitrary element in the image of a homomorphism, then its inverse element will also be within the image of the homomorphism. Okay, there will be another element in the domain group which is mapped onto the inverse of that element, basically, is what I've just shown you. Okay, right, so now what we have just completed then is that the image of a homomorphism is in fact a very special subset of the codomain group. Okay, it is in fact a subgroup of the codomain group. Okay, now what does that mean? Well, that means that if we are dealing with a non-surjective homomorphism, we can always reduce that homomorphism into a surjective homomorphism. So let me explain what I mean here. So let's say we have some homomorphism phi, which maps G onto G' as usual, and let's say this homomorphism is non-surjective. Okay, what I wanted to show you now is that I can always reduce it into thinking in terms of a surjective homomorphism, and I want to show you how we can do that. Okay, so let's suppose this homomorphism at the moment is non-surjective. So let me draw a picture for this. Okay, so here's our domain group, here is our codomain group here, and now the homomorphism is not surjective, so now the entire group here will be being mapped onto a subset of our codomain group over here, G prime. Okay, right, so once again I'll color code this in, so we'll have our domain group in red here, and we'll have our codomain group here in green, and now the bit that's actually getting elements mapped onto it is here in yellow, if that shows up. Okay, and that's the image of the homomorphism, and I've just shown that that is a subgroup of the codomain group, capital G prime. Okay, so here's the idea then. Why don't we just chuck away all of this bit? Chuck away this bit, and instead of viewing the homomorphism phi as being from G to G prime, instead just view it from being from G to the image of the homomorphism. Okay, so my idea here is we know that the image of the homomorphism is a subgroup of G prime. What if we just forget that G prime even exists and just look at this subgroup, the image of the homomorphism? Because after all, that is a set, okay, and it has a composition law on it, so it is in fact a group. My idea here is just forget that it's a subgroup. Okay, all subgroups are fundamentally groups. We know that, okay, they are just groups inside of other groups, but if we throw away the rest of the larger group and just think about this as a group in its own right, okay, we can now say, think of this homomorphism as being from the group G onto the image of the homomorphism, okay. This would now be a surjective map, okay, just by very definition, because the image of the homomorphism was all elements in the codomain group capital G prime that had elements in capital G being mapped onto them. So that means that this has to be surjective, basically. Okay? And my claim is that actually this is still a homomorphism between two groups. The image of the homomorphism is a group in its own right. I'm just saying forget that it's got the larger group around it and just think of it as a group in its own right. It certainly is a group in its own right. Okay, and this actually still obeys the homomorphism property that phi of A composed with B is equal to phi of A composed with phi of B for all little a and b are an element of the domain group capital G. Okay, and to see that, just ask yourself, how could that possibly not be true? Okay, because if you take any arbitrary little a and little b in capital G here, they are still being mapped onto the exact same thing that they were being mapped onto in this original homomorphism. Okay, all I've got rid of is all of the elements in this larger group, capital G prime, which had nothing to do with this homomorphism. They were the elements that did not get any elements in the domain group being mapped onto them. Okay, so how could getting rid of those elements possibly affect this condition? The answer is it can't, basically. So this mapping here, which is just this mapping where we've got rid of the elements that aren't involved in it from our codomain, okay, is still in fact a homomorphism, basically. So what I've just shown you then is if you start off with a non-surjective homomorphism, what you can do is you can reduce it into this very much so related homomorphism, in fact the identical homomorphism, where you've just changed the codomain so that it's restricted now down to the image of the original homomorphism, basically. Okay, and now it is a surjective homomorphism, so this homomorphism here is surjective. Okay, so you can always think about reducing a non-surjective homomorphism into a surjective homomorphism from the same domain group, but now onto the image of the original non-surjective homomorphism, which is a subgroup of our original codomain group then. Okay, right, and this is why homomorphisms which fail to be bijective because they're not surjective are not particularly interesting because you can always reduce them into this homomorphism that is surjective. And if the original homomorphism only failed to be bijective because it wasn't surjective, i.e. it was injective but wasn't surjective, then this new mapping here will now be surjective and injective, so it will be bijective, so it will become an isomorphism basically. So if a homomorphism is not surjective but is injective, then it's just basically an isomorphism of the domain group onto a subgroup of the codomain group. Okay, which is why I said that wasn't particularly interesting. After all, they could be reduced into isomorphisms basically. Okay, so this is the reason basically that from now on we are going to throw away non-surjective homomorphisms. We are just going to look at surjective homomorphisms, because if your homomorphism is not surjective, you can always just think of it as a mapping from the domain group G onto the image of the homomorphism rather than the full codomain group G prime. And this is basically the exact same mapping. You've just got rid of the elements in the codomain group which weren't involved in the mapping in the first place. Okay, so from now on we're just going to talk about surjective homomorphisms. Okay, so that means that if we've got a homomorphism that is not bijective, the reason that it fails to be bijective is that it's not injective basically. It's not one-to-one. Okay, and that becomes a more interesting thing to study. Okay, right. So, before we go any further with the abstract theory of homomorphisms, I want to give you a concrete example of a homomorphism. Okay, and then we'll study another little nugget of theory. We'll talk about the kernel of a homomorphism. Okay, but firstly then, my example of a homomorphism, okay, that is not an isomorphism, so it's going to be a homomorphism that is surjective but is not injective. Okay, so my example then, I am going to map the group of integers under addition, okay, which I'll write like so. So the set of integers with the operation of addition, and I'm going to map it onto the group or onto a group that is isomorphic to S2, and it's a form of S2 that we have seen before, the symmetric group on two elements, a very, very simple group. Okay, so I'm going to map the group of integers under addition onto S2. Okay, so let me just remind you of these two groups so that everyone's familiar with them, and I'll talk about the form of S2, or the realization of S2 that we're going to be using. Okay, right, so the group of integers then, okay, the set is the set of all integers, okay, so the set of all whole numbers, so you'll have 0, 1, -1, 2, -2, 3, -3, etc. Okay, and then the composition law that we have on this is going to be addition basically. Okay, so you'll have a massive great composition table. After all, this set of integers is an infinite set. Okay, so you'll have a massive great composition table which defines what any two integers added together is equal to basically. Okay, so we've called a composition addition in this case. So you can add any two arbitrary integers x and y together, okay, and the answer will be in this great composition table. So here's our arbitrary element little x, here's our arbitrary element little y, and we'll have the answer x plus little y in our composition table here basically. Okay, and this does obey the axioms of group theory. Okay, it's closed. Whenever you add two integers together, you end up with another integer. So all of the entries in this massive great composition table are elements of this set. It does obey associativity. Okay, if you want to know what is x plus y plus z, so the composition of three things, it doesn't matter where you put the brackets. You can either put them, and I'll do this with colour, you can either put them around x plus y and do x plus y first and then take the answer and add it to z, or you can put the brackets around y plus z and firstly add y and z together and then take x and add it to the answer of that. It does not matter, the answer is the same. Okay, so it does obey associativity. Okay, it has an identity element which is 0. 0 will add to anything to just give that anything back again. Okay, and we have inverses, so for any element there is another element which will add to it to give the identity element 0. Okay, that's just the negative version of that element. So if you've got an element little x, then the negative of that is the inverse basically, and those two will add together to give 0. Okay, so for instance for 1, the inverse is negative 1. Okay, for negative 2, the inverse is then 2. Okay, so you could go on basically. All elements do have an inverse, an additive inverse, so it's very nice. Okay, it's even an abelian group because it doesn't matter which way round you add two elements together. X plus y is the same as y plus x. Okay, so that's the group of integers under addition. Now let me show you the form of S2 that we're going to be using. So the form of S2 that we're going to be using will contain the two symbols +1 and -1. Okay, so this is a form of S2 that we've seen before, and when I say a form of S2, all I mean is what symbols are we actually using for the elements of the group and the composition. Okay, the usual form of S2 that we see is where we just have E representing the identity and tau as the other element. Okay, +1 is the symbol that I'm using for the identity, and -1 is what I'm using effectively for tau. We have seen this before, okay, and the composition in this case I'm going to call multiplication, okay, and I can write out the full composition table in this case because it's a very small group. Okay, so +1 is the identity, +1 times +1 gives you +1, -1 times +1 gives you -1, +1 times -1 gives you -1, and -1 times -1 gives you +1. Okay, so here is my form of S2 that we're going to be using. Here's the set of symbols, and here is our composition table here. Okay, right, so now to actually define this homomorphism then, okay, and you can see that clearly this homomorphism is not going to be bijective, okay, it is going to be surjective, it's going to be a surjective homomorphism, so it is going to be onto, but it cannot possibly be injective. I have got to map every single one of the integers onto an element in this set here. So I'm taking a finite set and mapping it onto I'm taking an infinite set and mapping it onto a finite set. Okay, there is no way on earth that that can be an injective map. Okay, so this is not going to be bijective, it's not going to be an isomorphism, but it is going to be a homomorphism. Okay, excuse me, so how am I going to actually do this mapping then? Okay, well, my mapping, the way I'm going to define it, is phi of some arbitrary element, little x, in the integers is going to either equal, of course, +1 or -1, and it's going to be +1 if x is even. Okay, so all of the even integers, so 0, 2, -2, 4, -4, they're all going to go on to +1. Okay, and of course all the odd numbers are going to then go on to -1. Okay, so if x is odd, I'm going to send it onto -1. Okay, so that's a perfectly valid mapping. It sends absolutely every single one of these integers onto an element in my S2 group over here. Okay, what we now need to check is that it does actually obey that condition of homomorphisms, that phi of A composed with B in the domain group. Now, what is composition called in the domain group? Well, it's called addition, so I might as well fill it in with addition here. So we want to prove that phi of A plus B is equal to phi of A composed with phi of B in the codomain group. Now, what's composition called in the codomain group? Well, it's called multiplication, so I might as well replace that with a multiplication symbol. So I want to prove that phi of A plus B is equal to phi of A times phi of B. I want to prove that this is true, basically. Okay, so how am I going to do that? Well, I'm going to split it up into 3 separate cases. So we'll start off with case number 1. Okay, so case 1 is going to be A and B are both even, basically. So we're going to start off with the case that both of these little integers that I'm taking, these arbitrary little integers, and I missed a statement here. I should have put for all little a and b are elements of the integers I need to prove that for. Okay, so I'm going to start off with the case that a and b are both even integers. Okay, are both even. I should stress that, so I'll put in an additional word there, are both even. Okay, right, so let's prove that this is true for A and B are both even. Okay, so if A and B are both even, then what is A plus B? Okay, if you add two even integers together, hopefully you are aware that you get another even integer back again. Okay, so A plus B, whatever it is equal to, is going to be another even integer if both A and B are even. Now, what does that mean that phi of A plus B is going to equal? Well, it means that it's going to equal plus 1 for all cases where A and B are both even. Okay, so when whatever little a and b you pick, as long as they're both even, phi of a plus b is going to be equal to plus 1, because a plus b is always going to equal an even integer. Okay, now let's check the right-hand side here. So that's the answer to the left-hand side. Now let's check what phi of a times phi of b is equal to. Okay, let's check that these are going to give the same answer. So, phi of a, if a is even and b is even, then both of these are equal to plus 1. So we are multiplying plus 1 by plus 1 in our group S2 over here. But what is plus 1 times plus 1? Well, of course, that's plus 1. Okay, so indeed it's worked. So whenever little a and little b are both even, this works. Okay, it's worked perfectly. Okay, but that's not always the case. It's not always the case that for any little a and b they're both going to just happen to be even. So we need to do some other cases. So case 2, okay, we'll do that both of them are odd. So we'll do both a and b are odd, are both odd this time. Okay, right, case 2 then. Okay, right, so once again we'll start off with the left-hand side of this equation then. So we'll consider what is phi of a plus b when both a and b are odd. So if they're both odd, whenever you add two odd numbers together, just do an example. 5 plus 7, what do you end up with? 12. Okay, you end up with an even number, and that's the general rule, that whenever you add two odd numbers together, it actually makes an even number. Okay, so whenever little a and b are both odd, it's always going to be the case that a plus b is even, no matter what little a and b actually are. As long as they're both odd, then this is even, basically. So again, that means that phi of a plus b is always going to equal plus 1 if a and b are both odd. So that's the left-hand side done. Now let's do the right-hand side. So we've got phi of a times phi of b here. Now if both little a and little b are odd, okay, then that means that phi of little a is going to equal negative 1, and phi of little b is going to equal negative 1, because odd numbers go to negative 1 under my mapping. So phi of little a and phi of little b are both negative 1. Now all I need to do is multiply those two together, but bravo, negative 1 times negative 1 is equal to plus 1 in my group S2. So that's worked perfectly as well. The left-hand side is equal to the right-hand side. Okay, so that's case 2. Finally, we have case 3. Okay, which is really two cases. Okay, case 3 is 1 is odd. Okay, so we've got 1 odd and 1 even, but I'm not going to tell you specifically which one is odd and which one is even. So either A is odd and B is even, or B is odd and A is even. It's one of the two. That's why it's really two cases, but I don't want to split it up into two cases. We'll just have it as case 3 together. Okay, right, so now let's consider the left-hand side. Okay, so 5a plus b. Now if we're adding together an odd number and an even number, and I know I've pointed at a and said that that's the odd one, and b that is the even one, but I didn't really mean that. Okay, it could be the other way around. B could be the odd one and a is the even one. It doesn't matter. Okay, when you add one odd number to an even number, you end up with another odd number. Okay, so an odd plus an even makes an odd. Okay, so a plus b is absolutely always going to be odd in this case, where 1 is odd and 1 is even. So that means that phi of a plus b is going to always equal negative 1 in case 3. Okay, so that's the left-hand side done. Now let's have a look at the right-hand side, phi of a times phi of b here. Okay, so one of these is odd and one of these is even. Okay, and again I'm pointing at examples, but it could be the other way around basically. So one of these is going to be negative 1 and one of them is going to be plus 1. Now it does not matter which one it is, because -1 times +1 is exactly the same as +1 times -1. Okay, and the answer to both of these is -1, as we know from our composition table. We're looking at these two entries here, basically. Okay, so because S2 is a nice abelian group, okay, these two answers here are exactly the same. Okay, right. So that means that the answer to the right-hand side is also -1, so it adds up to what it is on the left-hand side. It matches up. Okay, so that's excellent. We've done all the cases now, so I have proven that this actually is true for all little a and little b you could possibly dream up in the integers. Okay, for any little a and little b you dream up, it falls into one of these cases, and I've proven then that this is true. So this law is indeed true. This mapping that I have come up with is a homomorphism. Okay, it's a surjective but not injective homomorphism, so it's not bijective and it's not an isomorphism, but nevertheless it is a homomorphism. Okay, so now time for my take on what this actually means. What are we actually doing here? Okay, isomorphisms had this incredible meaning. Okay, they were these relabeling maps that turned one group into another. Okay, they were showing how two groups weren't actually that different at all. All you'd used was different symbols, but the algebraic structure was the same. What does this actually mean? Okay, well, the way I see it is that the algebraic structure here captures some of the very blunt truth of the algebraic structure over here. It captures part of the pattern here. It captures specifically the fact that two even numbers will always add to give another even number, two odd numbers will always add to give an even number, and an odd number and an even number will always add to give an odd number. Okay, that's what it's capturing. It's capturing part of the algebraic structure of this one. The way I like to see it is that what you're really doing is you're kind of like zooming out. You're seeing this algebraic structure in much less detail. You're seeing it far more blurry, basically. You're seeing it in much less detail, and you're seeing a much bigger algebraic pattern rather than the really detailed algebraic pattern that you have here. So that's the way that you should see it. If you've got a homomorphism between two groups, it means that the codomain group captures part of the algebraic truth in the domain group, basically. This is capturing part of the algebraic truth of the domain group, which is the group of integers under addition, basically. Okay, right, so we'll continue our discussion of homomorphisms in the next video, where we'll go back to talking about an abstract homomorphism rather than doing this specific example. Okay, and we'll discuss the kernel of a homomorphism.